Let's try out a worked example for sampling of signals. Here's our question. Consider a continuous time sinusoidal signal with two components. So our signal here is XAT, and it has two components, cosine and cosine. It has two frequencies. One is 5 pi, another one is 12 pi. So this basically means that it is a signal that has two cosine signals in it. We call these sinusoidal signals. So even though it's a cosine signal, but any signal that is either sine or cosine, they are both considered as sinusoidal, right? Part A is to determine the Fourier transform. And since this is a continuous time signal, we're looking for the continuous time Fourier transform equation. And then we're asked to sketch the spectrum of XAT. So XAT here shows that it's in the time domain. The spectrum of XAT is its Fourier transform. And its Fourier transform, if we follow our convention, should be capital X, A, J, capital omega. So here we use the term capital omega to link with a continuous time Fourier transform. Next, we're also given the sampling rate, which is 0.1 seconds. And then we're asked to determine the sampling condition. Sampling condition in this case is simply to find out whether aliasing occurs or not. Part C is to sketch the spectrum of the sampled signal. So we're sampling with a sampling rate of 0.1 seconds. We're sampling this original signal, XAT, with this sampling rate. Thus, we'll end up with a sampled signal. And then we're asked to sketch the spectrum of that sampled signal. In the previous video, we saw the sampling process. We saw that we'll have a continuous time signal, and the process of sampling is simply multiplying that continuous time signal to obtain the sampled signal. And it can be shown graphically when we have a whatever arbitrary signal. Multiply with a pulse train, that will give you your sample signal. These views are in the time domain. The same signal viewed in a different perspective is the frequency domains. So signals in the frequency domains are also considered. Multiplication in the time domain is equal to a convolution in the frequency domain. So if we look at the frequency domain graphs, we've assumed the spectrum of the original signal to look like that. And we perform a convolution with the spectrum of the pulse train to obtain the spectrum of the sample signal. We also see here some terms. XA J omega is the spectrum of XAT. P J omega, this is capital P, J omega is the spectrum of small p of T. Capital X of P, J omega is the spectrum of small x pt. Okay. So these are views in the time domain as well as the frequency domain. And signals in the frequency domain are also known as spectrum. Related, of course, by the continuous time Fourier transform. Let's go through the questions one by one. First is to determine the continuous time Fourier transform, and sketch out the spectrum of xa of t. You must know first that cosine and sinusoid signals, okay, in the time domain, let's say this is x, let's just say xt. If we have a cosine signal, it has a Fourier transform that will give you capital X j omega of a pulse. Okay, but where is this pulse located? This pulse should be located wherever the frequency of this signal is. If this signal has a frequency of 2 pi, for example, then this pulse will be located at 2 pi. And we don't just have one pulse, we also have its pair, P-A-I-R, okay? It's pair pulse located at negative 2 pi. And its magnitude, if this is simply plus minus 1, this magnitude will be pi, okay, for a cosine signal. So that written in equation form would be, in the time domain, cosine 2 pi, for this example, 2 pi t, and then its Fourier transform will be, okay, of pulses. You have delta, so a pulse is written as delta. Where is this pulse located? It's located at 2 pi, so minus 2 pi. That's just one pulse. The pulse on the negative side of the frequency scale, you have to add that as well. So plus delta omega is located at minus 2 pi, so plus 2 pi. And don't forget that the magnitude is pi. Delta has a value of 1, so but since this magnitude is pi, you have to multiply all that with pi. So that's how it works out for the continuous time Fourier transform of a cosine signal. So how does that relate to then our question here, where we have two signals? Let's assign this to be omega 1 and this second component to be omega 2. Okay, let's have my frequency domain graph here. So it's good practice for us to write down, to draw out the sketch with 0 in the middle for spectrums. Then you write down the name of the spectrum. This in this case is XA, J omega. And we have here is omega t. Let's tackle this omega t for the moment. Omega t is your sampling frequency, which is given by 2 pi ft. Ft is your sampling frequency, which is also given by 1 over t. So you can write this as 2 pi 1 over t, where t here, this is your sampling time, which we were given before. And this is substituting the value of 1 over t. This will give you 1 over 0.1, and that will give you 20 pi radians per second. We'll come back to this a little bit later. Just put it on there just for you to figure out why this is here. So to draw out our two spectrums, okay, there's the first one and second one. Oops. Okay, let's handle the first one, omega 1. So you can see here the frequency is 5 pi. That means you will have a pulse located at 5. So it is kind of helpful for you to scale all this as close as you can. You don't have to be so exact, but it does help. So that's 10 pi. If you know that this is 20, this is 10. Thus that will make this minus 20 pi. And over here, minus 10 pi. So 5 pi would be here. And I think you get the picture. I'll just put a few more scales here and there. Because then you can easily see that with cosine 5 pi, you will end up with a pulse located at 5 pi. That's one pulse. Let me try and make that a bit more exact. Right, there we go. Whenever you put one pulse, please also remember to put its pair on the negative side and its magnitude. This will be pi because the magnitude of the first cosine component is 1. Here will be simply pi. To differentiate it, okay, we have the second cosine component located at 12 pi. So 12 is somewhere here. Oops. And you see, oh, here we go. You see I'm putting it a little bit higher because we have 2 here. Over here, this is located at 12 pi. And the magnitude here, instead of just pi, will be 2 pi because of the magnitude 2 in the second sinusoidal component. And as before, when you have one pulse, you must include the pair. So if you see my convention here, I put the first or positive spectrum as a solid line and its pair to be a dotted line. Okay, so this here is your answer to determine the sketch of the spectrum. If you need to write down the equation, so as you've seen us write the equation over here, we're gonna do the same. Let's make some space. For the CTFT equation, we can write it down as xa of t, its Fourier transform will be capital X a j omega, and we can write that as cosine component, so it will be RG. Let's try to write it down as color code. So I'm writing on the blue color first over there. That's delta omega. This pulse is located at 5 pi. So this will be omega minus 5 pi. And you have its pair located on the negative side. That's delta omega plus 5 pi. Magnitude is pi. But we also have to add, since our signal has two sinusoidal components, thus the spectrum is also actually a combination of both. So here we have to write down delta omega minus 12 pi plus delta omega plus 12 pi for its pair. And additionally, its magnitude is 2 pi. Okay. And that's your answer for the CTFT as well as the spectrum. That took a bit too long. Now let's move on to part B, which is the sampling rate. And to determine the sampling condition, we're looking at the Nyquist sampling rate. And the Nyquist sampling rate simply states that your sampling frequency should be at least double the maximum frequency of the signal. So here you have two components. We have to test both of them. Let's assign one of it to be omega 1 and the second one to be omega 2. And let's calculate all these values. So omega t as calculated just now was 20 pi radian per second. And with omega 1, with a frequency of 5 pi radians per second, thus 2 omega 1 is simply 10 pi. And then we test omega t with 10 pi. Yes, omega t is definitely larger than 10 pi. What we can conclude from this is that omega 1 is sufficiently sampled. Or we can say oversampled. And that's good. This means that aliasing will not occur on omega 1. Let's test again for omega 2. Omega 2 is 12 pi. As such, 2 omega 2, as what we're trying to test over here, is 24 pi. Thus, the Nyquist sampling rule would state that to test with 24 pi, it should be over, but unfortunately in this case, omega t is less than 24 pi. Here we state that omega 2 is undersampled. That means sampling is not enough. Thus, we can expect aliasing to occur. Aliasing is expected to occur on omega 2. All right. That's it for part B. Let's move on to part C, which is to sketch the spectrum of the sampled signal. How I'll approach this, just for your understanding, is to sketch the spectrums separately. Because here, unlike before, now we're supposed to sketch the spectrum of the sampled signal. So I'll show you what I mean by this. So let's take the spectrum of the first signal. Let's call this part x1t with a frequency omega 1. Let's call the second part x2t with a frequency of x2. So this graph, let's draw one at a time. Let's draw x1 j omega. So as you know, capital X1 j omega is the spectrum of x1t. Let's start by drawing the spectrum of the first component, x1 j omega. So its spectrum, as we drew out previously, is simply a pulse, or two pulses, located at 5 pi and negative 5 pi. Now, what did we learn in the previous lecture on spectrums upon sampling? So the original spectrum before sampling only occurs once. But because we sampled the signal, because we sampled it, this original spectrum will repeat itself. So it will repeat itself about every omega t. So these two signals, located at negative 5 and 5, centered at 0 will repeat itself here at omega t. So these two signals will appear again at 20 plus 5. So over here is 25 pi. You'll see that solid pulse. And at 20 minus 5, which is 15 pi, you will see the pair, the dotted line pulse. Magnitude is still the same. So this happens whenever we sample a signal. Automatically, without sampling, you will just see the original spectrum, but because we sample, it will repeat itself. And it won't just repeat itself every 1 omega t, it will repeat for all omega t. So at negative omega t, you will see this as well. In actual fact, at somewhere here, there might be 2 omega t somewhere here. You will see again these two pulses. Okay. I simply draw these 3 dots to signify that they are signals that are repetitive for every multiple of omega t. So this is what happens whenever we sample a signal. This is what happens, and we can see this in the frequency domain only. Now I'll draw out the graph or the spectrum for the second component. So that's x2 j omega. As you can tell, this is why it's important for us to draw out the scale for omega t as well. So in our part A, we drew this out to be located at 12 pi, that's somewhere here, and then the magnitude is a little bit higher, at 2 pi. This is located at 12 pi. And this is minus 12 pi. Right. What happens here? Remember that this is now a sampled signal. The original signals are here, but because these two, the original signal has been sampled, these two will repeat itself. Remember, for all sampled signals, the spectrum will repeat itself. Okay, original spectrum centered about 0, it will repeat itself again here. So where is it going to be? It's going to be 20 plus 12. So somewhere here at about 20 plus 12, 32 pi, you will see a solid pulse. And then 20 minus 12, which is 8 pi, or somewhere here at 8 pi, you can start to see that this is a problem. This is what we call aliasing. This is your alias signal. And again, you don't see this repeating once. You will see this again at solid line here. This would be 8 pi. And another one somewhere over there at minus 32 pi. You get the gist. So this is the problem of aliasing. We don't like this. Aliasing is usually something we want to avoid. Right. So these are the two spectrums of each of these two components separately. If we are to sketch the spectrum of the entire signal, these two signals have to be added together. We have to add these two together, and what will we get? Okay, let's draw out the added signal. The added signal would simply be x. We'll call it x p j omega. Okay, recall that we use the term p here to signify that it's been multiplied by the periodic pulse train, which makes it sampled. So to combine the two, we have to draw out both on the same scale. We have your 5 pi and negative 5 pi. Oops, I forget I always forget to put this 3 dots. Please remember to put the 3 dots. That is to signify that the signal repeats. I'm drawing it with color coding so that it is clear to see which components are which. All right, so generally that's it. This portion here is the answer for the question. That is the spectrum of the sampled signal. And you can see from this question that aliasing has occurred, and because a signal has entered the domain of a different signal. And this is an issue when we try to convert this back from frequency domain back into time domain. So I'll take the graph that we've drawn previously, and then we want to, let's say we want to convert this. This is a x, p, j, omega. We want to convert it back into, by applying inverse Fourier transform, back into x, p of t in the time domain. But you can see what will happen here is that only information between these two values will be converted back proper. So recall that every pulse and its pair is equivalent to a sinusoidal signal. Okay, so a pulse in the frequency domain is equal to a cosine signal in the time domain. So this signal at 5 pi will give you cosine 5 pi t magnitude 1, because let me write that down here. This is pi, and then this red one here, this would be 2 pi. The red signal similarly is cosine 8 pi t, and magnitude is 2. So magnitude doesn't change, but you notice here the frequency is different. It's 8 pi. We started with 12 pi, but because we sampled it with a sampling rate that is insufficient, we end up with a different frequency. And that is the problem with sampling with a sampling frequency which is insufficient. So I guess that would solve or conclude our work with this example.